My name is Streich, and I'm a software developer at R3. Currently, I'm involved in the team that is responsible for evaluating the new technologies at our platform. But during my 3 years at the company, I was involved in many privacy features, identity management, and networking as well. So today, I will talk to you about high-level overview of the current state of Corda and how we imagine implementing zero-knowledge proof technologies in our platform. So for those who don't know, R3 is a company that started around 5 years ago as a consortium of banks and financial institutions that wanted to experiment with the blockchain technology, like different platforms. But during this evaluation, the founders realized that there is no platform that really meets the needs of the enterprise users. So this is how they decided to develop in-house product, which is Corda. It's the third biggest DLT platform out there. And it's written in Kotlin. It's entirely developed in-house at R3. You can write your smart contracts on Corda in any JVM language, but we target mostly Java developers. And the platform is open source. You can go play around with it or contribute at this address. So what I will talk today about is, first of all, the overview of Corda data model. Second of all, about transaction validity. It is important to understand how we can leverage the zero-knowledge proof technologies in our platform, as well as privacy in Corda. Briefly about SGX, and then I will talk about our use cases and how we can adopt the research that you're working on. Okay, so Corda uses classic unspent transaction outputs model. We have immutable states that can be of any type, so it's a very flexible programming model. And we consume them using the transactions. Like in this case, we have transaction that takes cash input, bond input, and outputs cash and bond as well. Transactions are validated using contract. So contract is just an ordinary JVM based language. In this case, Kotlin, but it can be Java, Scala, whatever. Class that has verify function that takes the resolved transaction, ledger transaction, and checks some invariants on it. So in this case, we check if the inputs are not empty, if outputs are size 1. This is the issuance verification. So states and contracts with the workflows are called Cordapps in our terminology. Okay, so how do we provide the uniqueness consensus? We use special nodes on the network that are called notaries, and they check for the double spend. And we have validating and non-validating nodes. Validating see everything in the transaction because they need to verify the transaction. Non-validating, they use special privacy feature that I will talk about on the next slide that shows only inputs to the transaction and hides the rest, but you cannot really check if the transaction verifies, which will be later problematic, right? Because you can block the states this way. So for privacy hiding, for non-validating notaries, we use partial Merkle trees. We shape our transactions as a Merkle tree with the subtrees for each type of the component. So we have like inputs, outputs, comment data, attachments, notary, and different fields in the transaction. And we hash it together Our transaction ID is the root of the Merkle tree. So this is pretty standard stuff. If we want to hide part of the tree, in this case, this diagram shows how to hide anything but command data and command signers. We just perform like a partial, we do a partial Merkle tree. And we call this privacy feature tariffs. And so to recap, what makes the transaction valid on our ledger? So first of all, contract verification. Second of all, we need to have signatures from all the participants in the transaction, right? And then a notary signature. The Merkle tree has to verify, and we need to verify also the backchain, which is another privacy issue in this case, right? So what is the backchain? So when we get the transaction with the cash, we need to check that this cash wasn't created out of thin air, right? So we need to walk the chain of the transactions back to the issuance transaction. And it is fine because in like non-fungible assets that are not that often traded, right? Because Corda privacy model is like data shared is on need-to-know basis. However, with very fungible assets like cash, it might become a problem because in the end you can see the whole transaction graph, which leaks information, and it's not good. So how do we solve it right now? We use Intel SGX, Intel Software Guard extension, which Kostas already mentioned before. And it's a way to offload sensitive data processing to remote untrusted machine. It's a hardware-based solution, and which protects the code running inside the enclave from the higher privilege process. And we also have implemented the remote attestation protocol to integrate with the Corda nodes. Why we decided to go with this, it's mostly because of the practical concerns. SGX seems to be more mature technology right now, and we have really aggressive timelines. Also, we have research team based that are free that already has released SGX SDK that lets you write your enclaves in JVM languages. It's version 1.0, and we are on our way to integrate it into our network. So also because our programming model is so flexible, and like people at banks or financial institutions are used to writing code in Java, for example, and there are domain experts in finance, but they're not domain experts in writing secure mathematical code, right? So this is also a trade-off we had to make. Another nice feature is that if you have trusted enclaves on the network and you have signatures from them, you don't have to walk back the whole chain, right? Because it's sufficient to have just the signature on the transactions that contribute to the current transaction, right? So you can check just that. But all of these privacy problems are also the problems that could be solved with zero-knowledge proof technology. And we are aware that at one point we will introduce it, right? So currently, even though we use SGX, we are designing our platform, so we will adopt also the zero-knowledge proofs. Because it is basically the same use case as SGX, right? We want to just prove that some computation was done correctly on the secret data. So as I mentioned before, there are 3 use cases. Actually, I mentioned 2 use cases, but there is also a third one that we could apply the mathematical techniques to our platform. So first, backchain validation. Second, non-validating notaries, which also, interesting enough, last week I attended the conference talk by ING team that did a small POC on using non-validating notaries, which it will be interesting. They're speaking later, and oracles. Oracles are also special nodes on the network, similar to non-validating notaries. We just show them part of the transaction and assign over this like command data, like a piece of information that it was valid at this time. Okay, we want our proofs to be non-interactive because anyone on the network has to verify it, which is obvious. And we currently are thinking about trying to evaluate the approach using one of our stable Cordaps. Probably Token SDK seems the best choice for that. However, we see certain issues with the adoption, and I will talk about that now. So, to be able to integrate zero-knowledge proofs into our platform, we need certain tooling, we need to solve certain problems. Also, these problems are regulatory or organizational, right, in enterprise companies. So, first of all, we cannot really expect normal Java developers to write code for these zero-knowledge proofs, right? So it is like a little research project idea because, I mean, we need a compiler, right? So you could theoretically use the GraalVM intermediate representation that already converts bytecode to graph in static single assignment form, and that's really aggressive memory read-writes optimization. So it seems like a good start for code flattening, and also it is a win if we manage to do something like that because we get many languages that are running on JVM. Right, so you do this work only once. However, there's another problem. You can only do it on restricted subset of bytecode, right? And funnily enough, we have a project that already tackles this problem. So we have a research group working on the deterministic JVM. So it comes from the SGX usage because we need to know that for every node in the network, the transaction has to be valid, and it can be different output depending on the environment, right? So what we did, we built the custom JVM sandbox that uses static analysis and some bytecode rewriting. And it also comes with really neat IntelliJ plugin that shows you, like, for example, you cannot use that. So yeah, like basically we try to limit our contracts to a pure subset of Java. So we remove any non-determinism like I/O files, network, random number generators, time. Okay, so another thing with the adoption, and we did some brainstorming with Mike recently, is the trusted setup. And it seems that protocol like Sonic with the updatable common reference string is a good choice for our networks. Why is it so? Because when you want to join Corda network, you need to go through the certificate authority. So we know that the participants in the network are well vetted. They will behave. So we already have some infrastructure in place for that and for distributing the network map. So so there's low possibility of Sybil attack on the network in this case. However, if we wanted to do that, we still need to have some maybe guidance on how to do it correctly in terms of the infrastructure. Okay, so another thing with the adoption is signature validation. So these are cipher suits supported by Corda, and they are like supported by the security experts in financial institutions, right? But the signatures algorithms that are ZKP friendly are not that well known in the environment, right? So definitely there is a need for standardization and another, like, again, guidance. So there are many factors that are taken into account. For example, compatibility with HSM vendors. It's not a thing easily overcome. Which leads to algorithmic agility as well, because in our case, it is part of the consensus. So we will need a global upgrade to all nodes. So the same with ZKP protocols, that because the research in the area is really fast, right? It moves fast, and we need an upgrade path. So in particular, we would have to be able to verify proofs with the previous algorithms, for example, right? And last and not least, it seems it is a it is a team effort. So we are developers, you're researchers, and you're working on really cool technology. But to be able to make it more wider integrated, we need good training and documentation. And when I did, for example, research for this talk, it is something we really lack. So it's not sufficient that I will come listen to your talks and learn a lot, but also we need other people in our team to be able to support, debug these solutions. So that's it. Thank you.
Are there any questions?
Okay.
Hi, I've been working on a plasma sidechain that would do similar operations to this. It's working almost exclusively in WebAssembly, which has solved some of the problems that the deterministic JVM would solve. So do you have any comparisons between those two environments, or is there?
I didn't work with this environment, so I cannot really tell. So, yeah. Okay.
What happens if you have a JVM security bug?
We need to upgrade, right?
Okay. But how do you ensure that balance wasn't violated during the time when that bug was active?
Okay, that's a hard question.
I tried.
Yeah, of course. I mean, so with the so you mean SGX, right? Because if we have like a validation in clear, you can revalidate the transactions, right?
Yes.
Okay, so like last research scenario would be like this. No?
Okay, if there are no more questions, let's thank the speaker once again.